So the next speaker is going to be Melissa Aldridge from UWA. He's working in maintenance, risk management, risk assessment, but PHP fellow, and currently working on ontologies for maintenance. And she's going to talk about cost-effective engineering design.
Right. Thank you very much, Marcus. Okay, good afternoon, everybody. Thank you very much. I was absolutely thrilled that, especially with both the earlier speakers, because now you know all about the problems with maintenance and engineering and data. And also, you had a wonderful sales job from Manoj about digital thread architecture and semantics. And I'm actually going to talk to you today about semantics and ontologies. But if I put that in the title, you'd all have left the room. So I haven't. But ultimately, what I'm talking about is about standardization and automation of data in a very smart way. And I've given it this title, Onshoring Engineering Design. And the reason for the title will be at the end slide. So hang in there with me. I'm actually going to start with the valves. So many of you here, you work in the chemical industry, high hazard industry, offshore industry, valves are super important, right? And a typical kind of facility will have, 3,000 to 8,000 valves, and most of them are small bore valves. I think we did a count on a current facility, and 91% of the valves are 2 inches smaller, though there are a couple of big valves. But most of the attention with what I'm talking about here is the many thousands of small valves. In the design phase, every single valve needs what's called a valve data specification. And each one of these needs to be done by a person. It's currently largely done by a person. It's done by a person. And the generation of VDSs takes thousands and thousands of hours of highly qualified engineers' time. Not only does it take time to generate the VDS, but then, of course, because it's a critical high hazard industry, there's a whole quality control process in place around the checking of that, which also takes even more experienced people and additional time. And a lot of this work in a number of countries, particularly high cost countries like Norway and Australia, has gone offshore. This is the link to the title. The work is largely done on Excel spreadsheets. So this is a real life example. I do apologise to members of JIP 33. No offence intended here. But basically, the orange block basically says this is what I want, and the grey block is product, and does it match? And some poor engineer goes down and goes, is that within limits? Is that within limits? There's you have to check all these things because sometimes the product comes in with different units. We all know that happens. Sometimes the label's not quite right. What do they mean by some of the labels on the left? Is there a common understanding? And so on and so forth. The opportunity for human error, as you can imagine, is endless. And this is a quick picture of a VDS. Valves are complicated, really complicated. And the schematic on the left doesn't sort of do justice to it, but an example of from the Equinor TR2000s, which are all available online. So every valve that Equinor has, you can download and see what its VDS is. It gets really, really complicated. Every time you make a decision about a size or a class or a feature, you're in a different set of API or ASTM or ASME standards. Every time you make it's really incredibly complicated. It takes many years to train engineers to do this one. And this was put together by Runa Frostedt from Able, who's been a valve engineer for about 30 years. And we said to him, come on, Runa, give us a diagram of, what do you do when you do this specification? And this is his kind of map of all the different, to make one VDS, all the different documents he has to kind of consider. And I could see why he's as grey as he is. And so we have this ambition, which is longer. There's a part of an earlier story here, which I'll get to if I have time, between PCA, which is the Post-Caesar Association, a not-for-profit standards body in Norway, Able, which is an EPCM, DMV, many of you know, Equinor, Aker Solutions, and our group here at UWA, to look and see if we can develop an alternative way of doing this that leverages in development all of the skills and experience of the partners, but removes the human element. Just think about that for a minute. It's a very ambitious thing to do. And what we want to do is we want to demonstrate this by on a number of VDSs. We're going to develop an ontology model. And what we want to be able to do is to automatically answer two questions. One, does the valve design specification enable the intended behavior at the location? So given these process conditions, does the valve design specification allow us to meet those? And then the second one is, does the installed valve, the proposed valve make and model, meet the valve design spec? So if a vendor sends me a proposed valve, does that product meet? And we want that checking to be done automatically and at scale. So how are we doing this? Well, we start obviously with the data in the valve data sheet. We have also have to build a conceptual model, and I'm going to talk a little bit about that later on. Once we have the conceptual model, we can enter the data into a sort of conceptual model prototyping a package called Protégé, which is an ontology design support tool. And once we're happy with the way that the model works and the reasoning and the axioms in the model, we can translate the whole thing into the DMV-IO tool, which I'll talk about a little longer if I can, but essentially it productionizes everything, and we can use templates to do this at scale. So we do it on a small scale first, one valve at a time, and when we're happy that everything's working, we can do it at scale with some existing resources and infrastructure. And there are 4 keys to this work. The first one is we have a common industrial data ontology. This has been around for years. It used to be, for those of you in the industry, called ISO 1596 Part 14, fondly known as Part 14. And this has been used for a number of years for material master data management on piping. It is now being translated under a new working group and a new ID into a dedicated ISO standard. It will be published, I think, at the end of next year. I and Marcus sit on the committee for this if you have any questions. The whole idea of an ontology is it's a very, it's like a specification for Lego bricks. It's a specification of classes, and imagine language as being like a set of bricks. Each brick can, in order to be conformant, you had to have a certain size, you have to have a certain style, if there's little buttons at the top, has to be certain materials, only things that match the specification will fit together. Ontologies like that. They're the specification for how you express things, how we express what is an artifact, how we express what is a feature, how we allow certain concepts to be connected with other concepts. This is essentially what an ontology, this shared, explicit, machine-readable specification is. That is what IDO is. And this idea that you can, as long as you're conformant to IDO, I work with IDO and you work with IDO, and both of our data sets and the way we configure our data models conform to IDO, then my model will, stuff I do in my model will be interoperable with stuff you do in your model. And it's going to be an ISO standard. So key number 1, we have a shared common specification. We have an ontology that we are all using and which constrains how we build things in the data models. The second thing is these guys have been doing this for donkey's years. This is not we just thought about this 3 years ago and we're on a road here. The initial work on this has gone on since the late 1990s and has been funded up and down, thick and thin by the Norwegian government and other parties. So we got to where we are today really on the basis of people, individuals who've been doing this for a long time, and companies who've been doing this for a long time, and funding that's been around for a long time. And I think that's testament to particularly the Norwegian government's interest in doing this, because Norway is a very high cost country. Key number 3 is that we have the ability, once we do this, too often these sorts of projects stop with a data model and it's in protege and you can't scale it. It doesn't work for business. In this world, everything has to work for business. DMV have been developing this tool that allows us to use these templates to scale how we enter data and to do all of the modeling at scale, because of course running reasoning over these really large data sets takes a sort of computer infrastructure that can be a problem if you haven't really thought about it before. So we have all the parts of the puzzle there. And then the other part of the puzzle that's really important is we have a really big community for IDOs. So we have key players who've been part of this for ages. Obviously, the ones that are listed on as partners on the earlier slides, but in addition to Equinor and Able and DMV, we've got Siemens and Grundfos. Here in Western Australia, we've got our university here, UWA, and we've got Uni SA who've been involved as well. As far as supporting the ISO standard, that was voted on last year. We're on a rapid 3-year path to publication, and the countries that are supporting it, you can see there, Australia, China, Denmark, most of the big ones. And so going back a little bit along the themes of this whole session this afternoon, what we're trying to do is move from a documents-based approach. So what I'm showing on this slightly complicated slide across the top is really the various stages of the asset lifecycle model. I'm now going to confess that I'm a maintenance engineer. And you're thinking, why on earth is a maintenance engineer collaborating with a bunch of design engineers in oil and gas? Partly the oil and gas bit is obvious because they're so far ahead of the industry I actually work in, which is largely mining. Mining will catch up to this in about 25 years' time. So I'd like it to happen while I'm still working. So I'm working with the oil and gas industry. But so many of the problems I see as a reliability engineer happen in design. But they happen earlier in the life cycle. I need to go back and find that data. So we're at the forefront here of doing information extraction at scale from maintenance, work orders, and other documentation. But once we extract that data, we need to be able to deal with it in a machine-readable way. And that's why the ontologies are useful. So for me, this PLM, this product lifecycle, whole of asset lifecycle approach is really important to what I do. And we're trying to move around away from the fact that the jagged sort of the diagram you see at the bottom is what happens is the design engineers get going, they produce documentation, they hand it over, and all they do is hand over PDFs. All the information about how those PDFs were created, what was done there, it's gone, right? Well, it stays where it was. And the next group get it. And then there's a hand, and the next group get it. So you know what happens when we get to maintenance? Yeah, we have operational readiness. Fantastic. We're lucky if we even get the OEM manuals. And we start all over again. And this is just the way it's been. The problem a manifest for maintenance people, as you heard from the previous speaker. And what we're moving is from this documents, PDF, PNID, handover type thing to what we call an information model-based approach. So this idea that with a common understanding of the structure and how you represent data, that you can, at every stage of the life cycle, hand over an information model rather than hand over a PDF document. And you can kind of see from the graphic, I'm just using the IMA framework in the middle, which is the different aspects from IEC 81346. But the idea is that this model grows until you get to the right-hand side. And basically the maintainer, that's me, ends up with a nice bit of information on the right-hand side rather than the PDF documents that we're currently dealing with. And as a result, you can see from the grey graphic that we have information growing cumulatively through the life cycle with all of the benefits you can see that Magnus has listed on the bottom. So in closing, I'd like to obviously acknowledge all of the very wonderful and experienced people who I'm working with on this, and you can see the names on the board. I'd also like to invite anybody who wants more information about the industrial data ontology to contact me. I and Marcus as well are on the standards committee representing Australia on something called ISO TC 184 SC4, which is the industrial data standard. It has 770 standards. Many of them I've never heard of, but there's some that in Australia we're particularly interested in. And if you need more information on that, let me know. And I also lead the working group in Australia for this particular standard. So any questions? Thank you very much.
Struggling with the concept of
You wouldn't be alone there, by the
yeah,
way.
this I know that's a physical concept also, but like
It's very practical
yeah, you get to understand. Speaking as a process engineer operations,
Mhm.
what I do, one of the issues we faced was when you want to make a change, you manage a change.
Yeah.
Understanding the rationale behind the original design.
Yeah.
If this helps, does it help? If it does,
does.
that's fantastic.
Yeah, so the whole idea is that certainly at the end of the day is that all of those decisions you can capture and go back to them because you have machine readable way of doing that. That is the intent, to be able to know what was the context when you made that decision. That's certainly one of the reasons I'm in it.
Explain that. Just building a bit on that. You mentioned when this gets applied to mining in 25 years. So how easy is it to expand the vocabulary and all the extra data and then just, you know, is that a massive major new project or is it built in?
No, so right now we're used for the data. Everything has all the pieces, almost all the words you want to use or the labels you want to use to describe bits of equipment can either be got for most things, even in mining, from CHIFOS or from 1596 Part 4 RDL. So we already have these sort of semantic definitions. We give them numbers. So when you exchange information, you exchange your numbers. It doesn't matter what language you're using. We have all of that for mining. There are very few that we would need to add to that. So there's no stopping people, just in terms of if I want to describe, you know, what's the difference between a pump and a centrifugal pump. There are different labels for that. They already exist. You can look them up on the PCA RDL. I was explaining that last week to senior people in 2 major mining companies, and they're like, "Oh wow, we've just spent thousands or hundreds of thousands of dollars making a taxonomy, making a library." And I'm like, "Well, you could have gone and used something that's already used by half the world's oil and gas companies, and it's been around for 25 years. Oil and gas is just partly, almost totally because of the regulation, safety critical element, and the need for people to, in risk assessment, to have a common set of log failure data that they use on commonly labeled pieces of equipment for regulatory approval, invested in this a long time ago. And it's fantastic. And mining doesn't have that.
I remember years ago working on what is about to become a shutdown olefins plant at Port Botany as a graduate engineer, doing a plant shutdown with 2,000 valves, and the MDS had to check myself. That I got a like that. And it's amazing. That's in 1995 when I was doing that. So that's almost 30 years ago. Hasn't changed. And so that's fascinating that it hasn't changed. A related question, though, you've got the maintenance engineers or the shutdown engineers swapping out every valve in a massive plant, for example. Could you have a reverse challenge, which is if I've got the whole life cycle of all of that data, will I now just drown in a lot of unimportant information? So how do I work out which bits of that whole supply chain? Sorry, I'm using.
Yeah, no.
Is the stuff I really need to know as a shutdown engineer replacing 2,000 1-inch valves in the olefins plant?
Yeah. So I would say, in a way, I'd kind of love to have that problem. Think about the alternative. I have nothing and I can't find anything. Sure. I have too much and now I have to sit through it. All I would say is there are tools for that now. Yeah. And we're busy developing them. So we're not at that stage yet. With what we're doing here, the business case is so much around design. Yeah. You were asking about business value earlier. When Equinor built their material master data, for piping. So the early version of this was just piping. That was much more complicated. They estimated $100 million in savings from just one part of that project. So there's a lot of business value at this stage. It's going to take time to roll through the maintenance, but we have to get it right here at the design with this first stage to move on to the next stages. So we're actually a long way from your problem, I'm afraid.
No, that's good. That's right. And it's also very interesting that Equinor's and other, is it Norwegian companies?
Yeah.
That are leading the game here. 30 years ago, I was working at Imperial Chemical Industries, which you probably got a good memory of yourself.
Yeah.
And they invented many of those standardized processes of propping across plastic and oil and gas and stuff. Those issues, it's led by the forward-looking companies that are very good at this stuff.
Yeah, and it's helped by funding from the Norwegian government.
Absolutely. Right.
Okay, last question.
Sustained and continuous funding, by the way, just to make a bit of a plug.
Yes, thank you for that. Noting the extensive amount of work that needs to occur to have this happen, the rationale to me, from a business guy perspective, seems very intuitive. So I'm trying to understand, why hasn't this been done donkeys years? And so I'm trying to understand, is it just this specific technical or design issue that has hampered the industry to not adopt these types of things from earlier on, or other forces or barriers that will potentially impede the progress of implementation?
So I think the key is it's hard, and I'll be quick here, but we're like the fifth generation in. If we tried it once, if we'd given up after the industrial implementation of the High North project that they had at the beginning, this one fell over. They might have given up then, and we wouldn't be where we are today, but they came back and they got some more funding from the European Union, and they learned and they came back, and they learned and they came back. We have a tendency in Australia, if it doesn't work once, we go, like, it never work. And so in this case, the business case has always been there and they've known it, but the solution has been hard. And we've benefited from AI and a whole bunch of other things that have happened now. The time is now.
Thank you, Malena.